We all have questions. Big questions.
How big is the universe?
It's part of what it means to be a human.
How far away are the stars?
Joy to boat?
My name is Stephen Hawking, and I believe that anyone can answer big questions for themselves. So with the help of a few ordinary people and a team of experts,
where you are changes how we see the universe.
We are going on the ultimate voyage.
These distances are just getting bigger and bigger.
A quest to answer the greatest mysteries of the universe.
Right, let's blow this bad boy up.
Using the power of the human mind.
We made it!
Because anyone can think like a genius.
Where are we?
Where are we? That's a pretty profound question. If we didn't know where we are, we'd be like monkeys in a forest, totally unaware of our position in the cosmos. Fortunately, we humans know everything, from the shape of the Earth to its place in the universe. But how did we find out? I believe anyone can work it out. Let's see if I'm right. I've asked 3 ordinary people to come on a journey of discovery. They will have tools and equipment, and I want to see if they can grasp the true scale of the universe. With some fun experiments to find out where we are.
Where are we?
That's a really good question.
We're on Earth.
Yet there's more planets out there.
In my solar system.
In the Milky Way.
That's where I'm at.
But how do we know for sure? The first step is to measure our planet. How big is it? And is it really round? The volunteers don't know it, but they are going to find out the size and shape of the world right here in Nevada. They'll do it by tackling their first challenge. How flat is this lake?
How do you measure a flatness of a lake?
With a huge ruler. Or,
Yeah, she has a point, though. You need something that you know is flat to measure the surface of the water against.
Yeah.
This lake holds the secret to the size and shape of the Earth. But can the team work it out? To help them, they need a few tools.
2 feet, 7 inches.
First is a powerful laser, which projects a straight beam of light across the surface of the lake. Next, they'll need a boat.
Whoa, we just passed through it.
Yeah.
Joy to boat?
This is Kat. Over.
I want you to go at the front of the laser.
Roger. Now we're gonna turn a little to the right.
If the lake is flat, the laser beam and the water will always be parallel to each other. Seen from a boat, the beam would always stay at the same height above the water, no matter how far you travel into the lake. But does that happen? And can the team work out why? Time to find out. The boat has a whiteboard attached to it, which will be a target.
We're looking for the laser beams so that we can mark it on the whiteboard.
Oh, it's hitting off that.
And we made the first measurement, and I was pretty confident that we weren't going to find anything.
A little more to the right.
Almost there. Here we go.
They take their first reading 500 feet from the shore.
Okay, that was the height of it. Got it.
For the next measurement, they'll need to go much further out.
Okay, so now I need to go 3 miles away from the laser.
All right.
Awesome.
So 3 miles away, where is the laser beam? Remember, if the lake is flat, it would be the same height as before.
Kat, you have to go slightly to the left.
You said go slightly to the left? Yeah. A little bit more to the right.
Here we go.
I don't even think this beam is going to hit our boat. So we're going to have to measure it on something else. All right.
No idea. Considerably
Here we
higher.
go.
Oh, is that your measuring tool?
Do you see it?
Yep.
Can you mark it? Let me scooch it.
We made the second measurement, and my whole world fell apart.
It's like 6 feet.
Yeah.
Yeah.
It seems a lot higher.
Okay.
You got it?
Huh?
All right.
Just 3 miles away, the laser seems to have risen by 6 feet. But we know the beam is level. So that suggests that the lake is now 6 feet lower.
To see a 6-foot drop when everything looked flat to me was kind of mind-boggling. Definitely kind of shattered my perspective in about 1 second. It made me rethink what was going on.
Okay, let's get this box open.
All right.
Yeah.
All right, what do we have here?
Tripod.
It's like a tripod.
Now, instead of a laser, a telescope will enable our volunteers to look in a straight line to the lake's opposite shore. But that's not the only instrument they'll need.
We're wondering, okay, how we're going to get this next point if it's so high it's past our board.
Whoa!
Very cool.
Are we getting in a helicopter? This chopper appears out of nowhere. All right, that is awesome.
Just as the telescope replaces the laser, a helicopter takes the place of the boat.
I'll stay with the telescope.
Okay, great.
We'll go in a helicopter.
That's a plan.
Sounds like a plan.
Yeah.
All right, let's do it.
All right, we'll go ahead and lift off.
This is exciting.
I love that there are no doors. We're flying to Pyramid Rock. Do you copy that?
I copy that. You are flying to the pyramid.
The lake looks completely flat from up here.
If they are twice as far away as before, how much lower will the far shore of the lake appear to be?
Jim, we're going to be at the top of the Pyramid Rock.
I got him. Yeah, I have you on the telescope. Go ahead and land.
As it lands, it completely disappears from my line of sight.
Joey, are you still airborne?
Yeah. Can you see us landing?
The reports from the helicopter, they're still flying. But I can't see it. To wrap your head around it in that short a time was a little difficult for me. I was like, this is crazy.
We have landed in our position.
Okay, Joy, go ahead and lift off.
They plan to ascend until Jim can see them on the horizon. Then they'll tell him their altitude.
Let me know when you can see us on spots of the horizon.
I got him. Okay, what's your elevation right now?
All right, Brian, how many feet are we above the lake?
24 feet.
Woo! We made it! 24 feet.
24 feet, awesome.
24 feet is a lot higher than our other 2 points that we got. That was awesome. It was great.
So here I have those 4 different calculation methods, and you can see the equations right there. And here I have the 8 inches per mile squared estimate. Notice that the division by 12, so this is in feet. All of these are in feet. In this column, column G, I am showing the error, the amount of difference between F6 and B6. So I'm comparing against arc length, my chosen method. If you think you want to use one of these others, you think it's better to use the peak-to-peak version or the horizontal version, then you'd have to change that. And then in the last column, I have the error expressed as a percent. And there's division by 0 because there's no error here. Or rather, the value is 0. As a percentile. So this means 0.03%. And a negative number will mean that the value is low. So that's just what that means. So this tells you how good approximately your approximation is as a percentile value. So next up, over here on the right, I've made us a nice little curve that shows a comparison of these 5 different methods of estimating the amount of drop. And we'll see our 8 inches per mile squared sitting right in here in between the peak-to-peak version and the horizontal length version on the extreme ends there. And all the way out to 1,000 miles, this is a pretty good approximation. Okay, but yeah, 1,000 miles, maybe that's not far enough. Let's push it. Let's see what happens if we just go all out. And this is what we get. Interesting thing for me here is that the horizontal length method and the arc length method diverge by more than the arc length method does against the 8 inches per mile squared method. The takeaway here that was absolutely eye-opening for me is that the 8 inches per mile squared estimate is really, really good. How good is it? How good is it? So I might want to ask the question, how far out do you have to go before your error becomes 1%? It's like at this point we're at fractions of a percent of error. How far out can we go and still stay under 1%? So let's scroll down as the numbers increase to right here. The first time the number reaches a 1% error is at a distance of 1,400 miles. So this 8 inches per mile squared approximation is good to within 1% accuracy out to 1,300 miles and beyond. So that may sound a bit shocking, but there you go. That's the actual numbers. And I invite you to check it yourself and see if that isn't correct. Finally, that brings me to the last point that I wanted to make tonight. And that is, why am I talking about this? Why is this so important? Obviously, I think this is really enlightening. The comparison is so accurate. It is far more accurate than I ever anticipated. And I want to stress that because I have seen numerous different flat earth debunkers, so that's globers who specifically go out to debunk the myths of flat earth. And I have heard them say that 8 inches per mile squared is an approximation over short distances. And they have stressed that. And they say that 8 inches per mile squared is a parabola, not a sphere. That's a parabola, not a circle. It can't be right. It's definitely wrong. I've heard that many, many times. And I am telling you, if you are a debunker, if you're in the business of dunking on the flat earthers, it's time to be humble. It's time to accept, check your values, and realize that, no, this is a damn good approximation, and it holds out to 1,000 miles. So it's perfectly fine. If somebody wants to use 8 inches per mile squared, that's fine if they're using it correctly.
Flat earthers all say, I shouldn't see this thing, but I do, so the earth is flat. Then to justify this claim, you all say the same thing, typically with no context whatsoever. 8 inches per mile squared. None of you have any idea what this means. You can't derive it. You can't calculate anything with it. You can't make a prediction with it. You can't tell me anything about this value at all. When I point this out to you, you get very angry, and instead of answering simple questions, you just link me to a bunch of videos made by con men. Well, I'm sorry, friends. Those people are doing incorrect math, or lying, or both, and they are counting on the fact that you won't do any math at all to check up on them. 8 inches per mile squared is not a valid way to measure Earth's curvature. If you understood math, you would immediately see that this squared on miles is totally out of place. That's because this is a parabolic approximation. This is for doing calculations with a parabola. It's possible that you remember this shape from middle school algebra, but I wouldn't be surprised if you don't. As you can see, the Earth is not shaped like this. So where does it come from, and why do people use it? It comes from the Flat Earth Bible, Zetetic astronomy, and Flat Earth priests use it because they know it's not accurate. It gives them incorrect values that they can use to claim that they shouldn't be able to see something when in fact they totally should. There are dozens of videos on YouTube demonstrating this, several of which reference the actual formula that actually describes Earth's curvature, which as you can see requires trigonometry. Stop blindly repeating what you hear on Flat Earth videos and learn some basic math so that you can do these calculations for yourself.
Gotta love Professor Dave, right? You guys so annoying. So I can science that. I'll put that whole video, or not the whole video, but I'll put the link for the whole video in the description box. I encourage you to go watch it. He does go on to say, mention observer height. Simply put, what he goes on to say is this. If you use such a straight up 8 inches times mile squared with no eyesight level, at 3 miles, for instance, you're going to get a 6 foot, right? More or less, Stephen Hawking uses 8 inches times mile squared, but he used it incorrectly as he did not configure observer height. And that's what I can science that is saying, like, you have to configure in observer height, and he is absolutely correct. So if you remember correctly at the video real quick, they were at 3 miles, 31 inches high was the observer height. It was 1.97 miles to the horizon and 8.5197 inches in drop. If you want that in feet, it's 0.997. I'm sorry, 0.70997. Wow. Feet. So it wasn't even a foot of droppage, and they said it was 6. Right? Now, let's try some real quick. So they got the 6 miles. Again, even if that guy was 31 inches off the ground, we'll say for argument's sake, he was 15 inches, like a foot and a half off the ground. You're still only at 14 foot of drop, right? So a lot of guys will say, oh, it's a parabolic approximation. Here's a few examples of parabolic approximations. Yes, there's parabolas in with them. I don't know why I did that. Anyway, but most of these are not straight up parabolas, right? So you go to Wikipedia. Here's a parabola, right? Equidistant from the vertical line here, right? Which I believe is the vortex, if I'm not mistaken, or the focus. I don't know. Anyways, so let's do a bit of reading here. This is from Wikipedia. It says in mathematics, a parabola is a plane curve which is mirror symmetrical and is approximately U-shaped. It fits several superficially different mathematical descriptions, which can also be proven or proved to define exactly the same curves. So you can go on and read all this. I just want to get to some main points in here. I want to make this as short as possible, but I encourage you all to go to Wikipedia, read all of this. I mean, these are all the different topics. All right. So let's go to this section right here. This is a focal length and radius of curvature at vortex. So in this section here, it just goes over, there's a lot of circle relationships with a parabola, and I want everybody to see that. Like, you just heard what Icon Science that said. He put all the mathematical equations up. Go watch the video. He goes more into detail with it. I didn't want to put a 54-minute video in with this. It would be like an hour and a half long, and nobody's going to watch that. So, anyway, just wanted to show that there are circles in it. Here's a gallery. You know, it's the arc. This is like a comet or whatever. The arc and the bridge. You know what I'm saying? So just all examples of parabolas. Right? And then Mr. Hawkins flying in whatever that is. It's the zero gravity, the 0G. Yeah, 0G plane. Right there it is. Go0g.com.
This laser test was by D-Marble. In this case, the person holding the laser was at 7 feet, shooting the laser at a distance of 10 miles. At 10 miles under the globe model, the observer would have to be at a height of 30 feet in order to see the laser source. Instead, you can see the source of laser at just inches above the water. That water is flat, and the laser source proves that it is not being obscured behind the curvature. The liars have tried to confuse the issue by claiming that the laser wasn't level, but that's entirely irrelevant, since if the laser was angled downward, it would have hit the ledge curvature quicker. If the laser was pointed upward, then the observers would still not have seen the source, because the source of the laser would still have been hidden behind the alleged curvature. This footage would be impossible if we were living on a globe. Hello everyone. This video is primarily for the honest skeptics of the flat earth, but I hope that everyone will enjoy it. Despite how difficult it may be, I simply ask you, as an honest, objective, reasonable person, to set aside your indoctrination and belief in the globe, at least temporarily, and examine the evidence that I'm going to share with you today. I believe the flat earth evidence here is dispositive, and I think you'll find it compelling as well. Flat earth is certainly a very difficult truth to accept, because the ramifications are so great. But we do indeed live on a flat and stationary earth. According to the globe model, all bodies of water, including the Great Salt Lake, must have a certain degree of convexity to them. As Samuel Rowbotham wrote in 1849, if the Earth is a globe and is 25,000 English statute miles in circumference, the surface of all standing water must have a certain degree of convexity. Every part must be an arc of a circle. From the summit of any such arc, there will exist a curvature or declination of 8 inches in the first statute mile. In the second mile, the fall will be 32 inches. In the third mile, 72 inches, or 6 feet, as shown in the following diagram. I have continued the numbers up to 200 miles. All water must have this convexity if the globe was a reality. But this Earth curvature does not exist anywhere. Now, this laser test took place on Saturday, January 16th, 2021, at the Great Salt Lake in Utah, between Antelope Island State Park and the Great Salt Lake Marina. I was located here on the northwest corner of Antelope Island. My friend Robert from FE Corps was located here on the south end of the Great Salt Lake near the Great Salt Lake Marina. I have the coordinates listed for both locations. The total distance between the 2 points was 21.03 miles. We both had our cameras and lasers at around 5 feet above the water.
Hey everyone, this is Ben with Taboo Conspiracy. It is January 16th. Just about ready to hike out that way to get around the point there for doing a laser test around the bend there, and we're going to be shooting the laser off towards the marina across the Great Salt Lake. The date is January 16th, 2021, and what you're looking at is the Great Salt Lake from the Great Salt Lake State Park, so at the south end of the lake, and right there is Antelope Island. And our friend Ben is currently hiking to a point, northwestern point of that island, that as we calculate by Google Maps is 21 miles from this point here. So I'm going to scout out a place. It's a cold day. I'm going to try and scout out a place to set up a laser. Boat just went by, so now we get a bunch of waves, and you can see here Antelope Island, another island off in the distance there. There we go. And then back the opposite direction we have, there we go, the Magnus smokestack. Just getting ready to start shooting the laser once the sun goes down. I'll be shooting the laser that direction. Let me read you off the coordinates that I'm located at. My latitude is 41.037384. My longitude is negative 112.278569.
Here's a photograph of how my camera was set up standing in the water. Here's a photo of the laser. And here's the selfie. I also brought my two sons to manage the laser and the flashlight. Based on the globe curvature math, from an observation height of 5 feet and a distance of 21.03 miles, the curvature of the Earth should have been hiding 223 feet of the other shore. Here's another globe curvature calculator that reaches the same amount. In other words, Robert's laser and camera at 5 feet should have been 218 feet below the horizon if the globe was real. Or you could say, as another example, that Robert would have had to have been standing on something like this 218-foot cross to see my laser 21 miles away, or vice versa. That's huge. Do you see the door at the bottom there? But before I get to the laser, I wanted to share some other footage. Of course, I had to film the beautiful sunset. This is a great spot if you're like me and appreciate these views. I also filmed the Kennecott smelter stack, and you can see all the way to the bottom and to the beach. There is no Earth curvature there. This video is already impossible under the globe. If you are claiming that I'm looking at a mirage, then you need to tell me where the mirage ends and the real line of sight begins. Compare this still from Robert's video that shows the stack from his point of view. Of course, it was cold out there in January, and the temperature dropped rapidly as it got dark, but the biggest problem was the fact that I did not have phone service on that corner of Antelope Island, and so I had no way to communicate with Robert. I mistakenly thought Robert would have been in front of the lights. I was actually just about to give up when my son said that they spotted Robert's laser in the distance. Sometimes you miss those things when you're trying to operate the camera as you're looking at that little screen. But let's watch the video, and please forgive my giddiness when I see the distant laser, as I was pretty excited.
I see it.
Yeah, I saw that.
You saw what?
The little flash over there. It's like to the right of the lights, a little bit.
Yeah! Can you point over there? That was it. I caught it on footage just for a second. Then they probably turned it off. Keep. Oh, it's to the right of the lights. Interesting. See, I was looking in the wrong direction. You guys saw it with your naked eyes?
Yeah, I saw the blue over there.
That's awesome. Oh, there he is! I got it! Woo! All right.
So should I start trying to...
No, just keep aiming it over there. Try to get closer. Try to move it around in that area because you might get a direct hit. So think about it. You can see the reflection on the water. So did the reflection and the laser hop the curvature? Awesome. Oh, we got it.
Look at this still from the video. You can see that I have a direct line of sight as I'm looking straight at the intense source of the laser. I'm not seeing the laser from an angle. Also, notice the reflection of the laser on the water. As I said in the video, did both the laser and its reflection hop the curvature to present a false flat Earth? Where did the massive Earth bulge run off to? Unfortunately, because I didn't have any communication with Robert, we couldn't really perform any other tests. But here's Robert's video from the southern side. He didn't have a super zoom camera like the P900, but you'll still see my laser coming from the north. Matt from the Utah Flat Earth group was there to help Robert with the filming. Let's watch Robert's video.
Blue, blue. Okay, we're filming now because we've seen the laser a couple times. Oh, there it is! Yes! Yes, yes! Oh my gosh. Okay.
How do you zoom on this? Can you?
Just with your two fingers, just wide.
Okay, okay.
We tried that.
Oh, yeah, we can see it on camera.
Yeah.
There, it's coming from right over there.
Okay, I want you to get my laser to show so that people can see what we see is the laser goes out absolutely straight. So just get it right here and see the beam going out there. You can see there's no bending, there's no curving, it's not going down or anything. It's just straight as an arrow.
Yeah, it's a great shot of that.
You can see it reflecting in the water even.
If the lake is flat, the laser beam and the water will always be parallel to each other. Seen from a boat, the beam would always stay at the same height above the water, no matter how far you travel into the lake.
Just dot it. B-E-N.
I'm seeing something flash over there, but it's not blue right now.
Nah, I think it might be having a little. There it is.
There's the blue.
Did you get it in the camera?
Uh-huh, I got it in the camera.
Am I hitting him?
Yeah, you're pretty much right on now.
Yeah, see, I saw his flash up in the air there. I'm gonna try and bring mine up a little bit. See if.
I mean, now that I've zoomed in, you can't see anything else, but you can still see the blue. His blue flash.
His blue flash?
Yep.
Really?
Mm-hmm.
Great. That's 21 miles.
21 miles from
here to
Great Salt Lake Visitor Center Marina over to Antelope Island.
Yeah, the northern tip.
The northwestern tip.
Oh,
yeah.
In order to maintain the globe narrative, some globe propagandists will claim that the laser perfectly bent in an arc to match the Earth's curvature, but the claim is ridiculous. Obviously, I had a direct line of sight to the source of the laser here, and I had a direct line of sight with the base of the smelter stack. Nothing in the atmosphere causes lasers and images of distant objects to perfectly wrap around an imaginary Earth bulge so that the Earth bulge somehow disappears. I strongly recommend these videos from Dr. John D., who has a PhD, where Dr. John D. goes into much more detail regarding the impossibility of the arcing laser claim. Simply stated, this is not a mirage. I certainly had a direct line of sight with Robert's laser when it should have been 218 feet below the horizon. There is no Earth curvature there, and if there's no curvature over the Great Salt Lake, then there's no curvature over any body of water. Therefore, the globe is false. Yes, we were all lied to. Flat Earth is a humbling fact. I understand. I used to be a globe believer too, up until just 5 years ago. But there is freedom in truth. A big thanks to Robert from FE Core. Thank you everyone for watching.
Chemist and proponent of intelligent design James Tour wasn't a fan of the...
You know that I have not been a proponent of intelligent design.
And proponent of intelligent design James Tour. I just thought it'd be fun to have like a little persona, you know, Professor Dave. It's just, you know, a little name.
You know, I don't have a PhD in chemistry or anything, but I, you know, did work in, you know, I took courses with laboratory components as an undergrad, and then I did most of a master's in synthetic organic chemistry.
But I didn't really last long. I dropped out in my second semester. I wanted to move up to San Francisco and play music, and then I moved down to Los Angeles again for music opportunities. And but I eventually got this teaching job for organic chemistry at this little trade university. It was a pretty lucky break because with a bachelor's degree I was only supposed to teach the laboratory portion, but on the first day the lecture instructor had this freak out. He just took off, and so my boss came up to me and he said, look, you gotta go teach the lecture. There's nobody here. They offered me the job permanently, but contingent on me getting a master's at the same time. So I went over to Cal State Northridge to give a second shot at a master's degree in chemistry,
and found that I really hated it. I really didn't like it at all. Do not enjoy doing chemistry.
But through a bunch of bureaucracy, quite frankly, I lost that job, so I had to withdraw yet again from the master's program. A lot of you ask very incredulously, are you a real professor? I sit literally in this room like 60 to 70 hours a week, and I chose the name really without much thought. It was kind of tongue-in-cheek, to be honest. I just thought it'd be fun to have like a little persona, you know, Professor Dave. It's just, you know, a little name.